So today we're going to be working on section 9.1 where we introduce the concept of inverse and joint variation. Now the good news for you folks is that since we've already done direct variation, you'll find that inverse variation and joint variation are very similar in terms of how you use them. In each case, the variable k is the constant of variation. And the method for going through and solving a direct variation problem or an inverse variation problem or joint variation problem are all the same. The first thing you want to do is substitute for x and y. The next thing you want to do is solve for k, the constant of variation. And the last thing you want to do is write the equation. So let's go through some problems that will demonstrate how to do that. So in a direct variation model, I'm using y is equal to k times x. In an inverse variation model, I'm using y is equal to k divided by x. And in a joint variation model, it is z is equal to k times x and y. Okay, this is the only thing that really changes in the different problems. The methodology for solving remains the same. So the first thing I'm going to do is take x and y and substitute them into the type of equation I'm working on. So y was 84 when x was 12. So to solve for k, I'm going to take and divide each side of the equation by 12, and I'll find that k was equal to 7. Now I need to write my equation. Y is equal to 7 times x. So the process of writing the equation is nothing more than taking the constant of variation and plugging it into the original model, y is equal to k times x. If I do that with an inverse variation model, the only thing that changes is the model itself, but the steps remain the same. So I substitute in for x and y. So 8 is equal to k divided by 4. And then I solve for k by multiplying both sides of this equation times 4. So 32 is equal to k. The last thing I need to do is write the model. So y is equal to k, which is 32, divided by x. So that is my inverse variation model. Joint variation, again, is z equals k times x and y. I'm now going to have three values to substitute in. Z was 2 when x was negative 12, and y was 4. So if I continue to solve for k, 2 is equal to negative 48k. And if I divide both sides of the equation by negative 48, I'll get negative 1/24 is equal to k. And the last step again, write the model. Z is equal to negative 1/24 times x and y. And that's how you do a joint variation problem. Let's do a couple more examples. The key for you in doing this work is looking for the keywords in the instructions. You'll notice that here the variables x and y vary inversely. So since they vary inversely, I know that I'm going to be using the model y is equal to k divided by x. Okay? So this problem also brings a new type of wrinkle. First, they want me to write an equation that relates x and y, then find y when x is equal to 2. So there are two separate things I need to do. First, I'm going to write the equation. So I substitute y was 6 when x was negative 2/3. Now I'm going to multiply both sides of the equation by negative 2/3, and I'll be able to find k. So 3 goes into 6 two times, so k ends up being negative 4. And now I'm going to go ahead and write the model. Y is equal to negative 4 divided by x. So that's writing the model. The next thing it asks me to do is then find y when x is equal to 2. So I'm going to take that value of x, and I'm going to plug it into my model. This is nothing more now than doing an input-output table, basically. So when x was equal to 2, y was equal to negative 2. Okay, so these two answers comprise the solution to this type of problem. Let's do that one more time. So y was 1 when x was 7. If I solve for k, k is equal to 7. Now I'm going to write my model. Y is equal to 7 divided by x. And now I need to find y when x is equal to 2. So y would be equal to 7 divided by 2. Nothing more than that. No more simplification necessary. Doing joint variation, you'll notice that when we do joint variation, the problem is going to say the variables x and y vary jointly with z. We're going to do the same sort of thing where we're going to write an equation that relates x and y, and then find a specific value of z given two separate values of x and y. So our model again is z is equal to k times x and y. So z was 5 when x was 1 and y was 1/3. So 5 would be equal to 1/3 k, and to find k now I need to multiply both sides of this equation by 3. So 15 is equal to k. Now I'm ready to write the model. So z is equal to 15 times x and y. So there I've written the model. And now what I want to do is I want to solve for z when x is negative 4 and y is 7. So z would be equal to 15 times negative 4 times 7. Here's my solution for writing the model. So z would be equal to negative 4 times 15 is negative 60 times 7 is negative 420. And there we go. One more time doing the same thing. Z was 8 when x was 5/6 and y is 3/10. Okay, now I'm going to simplify over here to on my right side of my equation. 5 goes into 10 and leaves 2. 3 goes into 6 and leaves 2. And I end up with 1/4 k. And to solve for k, I multiply both sides of the equation by 4. So k is equal to 32. Now I'm ready to write my equation. Z is equal to 32 times x times y. And again, x is negative 4 and y is 7. So z is equal to 32 times negative 4 times 7. 32 times negative 4 would be negative 128 times 7 would be 56, 19, negative 896. Okay, so there are my two solutions. Okay, the way this works out in a word problem, here we have a problem dealing with heat loss. If I read through the problem, the heat loss, H in watts, through a single pane glass window varies jointly. Okay, so I know this is a joint variation problem. Varies jointly with the window's area and the difference between the inside and outside temperatures. So now they would like me to write a model. So heat loss is going to vary jointly. I know I'm going to have, we're working in this sort of a model, k times x times y. So heat loss will vary jointly with some constant of variation times the area of the window and the difference between the inside and outside temperatures. So I would have temperature inside and temperature outside. So H is varying, right? I've got a constant of variation jointly, so I'm going to have two different values multiplied together, the area and the difference between the inside and outside temperatures. So this would be the process of writing the model. Now I want to go ahead and solve this portion of the problem. A single pane window with an area of 1 square meter, so I know A is equal to 1 meter squared. And the temperature difference, so the change in temperature, right? Delta means change in temperature, of 1 Kelvin, has a heat loss of 5.7 watts. So I know then that the heat loss is H, 5.7 watts. Then they want me to know what is the heat loss through a single pane window with an area of 2.5 square meters and a temperature difference of 20 Kelvin. So the first thing I'm going to have to do is use the supplied values to find the constant of variation. So H was 5.7, A was 1, and the difference in these temperatures was also 1. So I'm going to find that my constant of variation here is 5.7. If I want to go on now and write the model, H is equal to 5.7 is my K value, times the area, times the change in the temperature. Now my new values for this portion of the process is that my area is going to change to be 2.5 meters, and my temperature difference is 20 Kelvin. Okay, so if I now multiply all of these out with my calculator, I'll be able to solve for H. And that's what we're going to do in section 9.1.